Myself Mintu Ghosh, HOD of Mechanical Engineering Department, Bengal College of Engineering and Technology, Durgapur. Extend my heartfelt greetings to one and all present on this online platform. And I welcome all to the final session of this 5 days program on recent advances in intelligent systems and smart technologies for core engineering applications from 10th March to the 14th March 2026. And this event is organized by the Departments of Core Engineering and Basic Sciences of Bengal College of Engineering and Technology, Durgapur, in collaboration with the Institution of Engineers India, Durgapur Local Center. I am privileged to welcome our esteemed resource person, Dr. Pradeep Kumar Roy, for this session on structure property relationship, advanced functional materials, nanomaterials, and sustainable materials for modern engineering applications. Dr. Pradeep Kumar Roy has completed his BTech and PhD in ceramic engineering from NIT Rourkela. He was associated with Compton Greaves Limited, Mumbai, for 6 years as deputy manager of R&D. He did his MBA in operations from United Business Institutes, Brussels, Belgium, during his industrial period. He started teaching career at BIT Mesra, Ranchi. He joined IIT BHU in 2014 as an assistant professor, and presently Dr. Roy is working as a professor in the Department of Ceramic Engineering, IIT BHU. Current research interests are in the field of magnetic, ferroelectric, and piezoelectric materials, nanomaterials, high temperature ceramics, and waste management. He has published 68 research papers in international journals, field 33 granted 20 Indian patents, and presented 77 research papers at national international conferences. He is the reviewer of more than 100 international national journals and conferences, and he is a certified chartered engineer by the British Council UK. He is also a fellow of Institution of Engineer India and the Institution of Electronics and Telecommunication Engineers. He has been promoted to the grade of IEEE senior member, and he is an associate editor of the Journal of Asian Ceramic Societies and an editorial board member of scientific reports published under the Nature portfolio, and is the member of editorial board of Indoceram and the Journal of the All India Pottery Manufacturers Association. Now I would like to hand over this session to Dr. Roy, and I am sure we all will be enriched with the knowledge and enjoy the learning. Now the session is over to you, sir. Please take the session in your way.
Thank you, Professor Mintu Ghosh. Thank you for your introduction.
Thank you, sir.
First of all, I'd like to thanks to the organizer, especially Gautam Uncle, who is sitting here also, for giving me this opportunity, as well as you two, to give this talk. But initially, I was confused that which topic I should start, because most of the peoples are from different background. I am the only person from materials background. So initially, I thought to give something else. Later, I shifted my talk on different area. Can my slides are visible?
Yes, sir. Now it is coming. Your screen is visible, but slides are not yet visible.
Now?
Yes, now it is visible.
Okay. But one thing I've noticed that the first speaker and the last speaker of this STTP is Professor Roy. Both are Professor
Yes,
Roy.
yes, sir.
So it was nicely organized. Thank you for this opportunity. And today I'm going to talk on some different aspect what my previous speakers has given in this FTT program, where I'll talk about that how the structure property relation in different advanced materials is actually correlated different modern engineering applications. And I'll give an example with the real problems, how industry is doing the research on advancement of the product with some different kind of technologies involvement. Now today I can talk about like it's not that only the materials engineer can do. Today almost all the research has shifted toward the interdisciplinary work. So it's not it's that is that only the materials contribution has done. It is done by the contribution of different electrical engineering, mechanical engineering, at the same time the materials engineering also. So today I'll talk about the product called surge arrestor, lighting arrestor, which is mostly used in electrical sector. And there I'll talk about how the materials development happen in that product and what kind of technology people have used, especially in the nanotechnology, to introduce into that product to improve the performance of that equipment. So in my talk, I'll start with the introduction of the equipment, which is I'm going to talk about, then the materials which is involved in that part of that equipment, and finally I'll talk about how this research involved to improve the performance of that equipment. Okay. So the product is called surge arrestor. Some people talk about lighting arrestor also, which is mostly used to protect any equipment or instrument from over voltage. There are two kind of surge arresters available. One is an electrical, one is an electronics application. So mostly I'll talk about here is the electrical aspect, not electronics, because the performance and the material aspects are almost same. The difference is only rating. The electrical sector, the rating of surge arrestor is a little bit high. It's mostly in kV range. But if I talk about the electronics, it is mostly in voltage range. I mean, some volt or some millivolt kind of thing. So that is the only differences. Now, when I talk about the over voltage, that over voltage are mainly two types. First is normally people talk about the temporary over voltage, which is mainly because of the earth fault and it survives few seconds. And second is the transient over voltage, which is actually either it's done by your switching or maybe it's done by for lighting. Switching mostly survive for a few milliseconds and lighting survive for some microsecond. Now here we mainly talk about the transient over voltage part, not the temporary over voltage part. Temporary over voltage part mostly we use electronics surge arrestor, but in transient over voltage we use electrical or high voltage surge arrestor. So when I talk about this high voltage, over voltage, this is basically in a spike. I mean, this is an impulse kind of thing. It has some rise at the same time it has a fall also. Okay. Now today, if you look at the application of this product, it's almost every area starting from telecommunication to industrial to almost all household applications. Everywhere this kind of product is used. Well, we are not developed country, but in developed country, almost in every switches also people are using such a resistor just to protect the devices from the over voltage. Okay, now there are two standards people follow in the surge arrestor. One is IEEE standard, which the symbol is something different, and IEC standard. IEC is mostly International Electrotechnical Commission. The standard, the symbol is little bit different, but the same purpose, which is used for the lighting arrestor or surge arrestor. Now in India, there are few companies who are manufacturing this product, like your Lamco, Elpro, Crompton, Oblum, and Erva. These are the 4-5 companies who are the major manufacturer as well as the major stakeholder of this surge arrestor in India. And I can talk about like India is the first, Crompton is the first company who introduces 1200 kV transformer in 2012. And earlier our, the transformer which was used was around 800 to 600 to 800 kV. Then they started 1200 and more than that. But to protect that equipment, they started the development of this surge arrestor. So that development I'm talking about here. So when I talk about this in a protection level, you can look at here that this graph, the first graph talks about the load is basically transformer and the protector is basically surge arrestor. So this transformer and surge arrestor, they are parallelly installed, okay, and they are connected with the high voltage, and both are grounded. So in normal operating voltage, the surge arrestor act as an insulator. There's no current flowing through the surge arrestor. Okay, so if any current is coming from transformer to the household part, that there is no leakage normally happen through the surge arrestor. But when as soon as the surge will come, this surge arrestor immediately converted into the conductor, and all the high voltage will passing through that surge arrestor, and in protect the normally the transformer, the heavy highly costly transformer. So here I am talking about surge diversion. So surge arrestor is mainly used for surge diversion, not surge suppression. In suppression, normally we make it in the in series, not in parallel. So I'm not talking about surge suppression. I'm talking about the surge diversions. So if I talk about the major function of the surge arrestor, so in normal operating condition, the surge arrestor acts as a purely insulator, so no current is flowing through that. And when the surge will come, immediately, I mean, there should not be any kind of delays for that. Immediately, it should convert it into the conductor, and all the current passes through the surge to the ground, and it will protect the devices. Now, during the surge, it is found that the temperature can go little bit around 120 to 140 degrees Celsius. So if the temperature is not dissipated properly, so sometimes it may happen like the performance of the surge arrestor is deteriorating. So in that case, the devices or the equipment should be thermally stable, and there should be some provision to dissipate that heat immediately after the surge will go back. So if you look at this figure here, it talks about that how far I should install that surge arrestor from the equipment or transformer. Okay, so this is normally called the protection level, and this protection level depend on the insulation level of the equipment. I mean, if I talk about some people talks about the transformer was blasted. So blasting is nothing but the insulation level of that equipment is actually vanished. Now it's become conductor. Okay, so based on that insulation level, there are few parameters which is based on the standard. This is actually constant also. So based on that, we can through this formula, we can use that how far I can use that surge arrestor from the transformer to protect from the surge. Okay. Now, if you look at the classification of the surge arrestor, there are two major classifications based on housing. One is the insulator based, and second is the rubber based. It's basically polymer. Okay. Now, mostly in polymer based, the product are very small range, small rating. It's mainly hardly around 100 k 72 to 100 kV surge arrestors are available. But in porcelain based surge arrestor, it can be goes up to 1200 also. So earlier it was 400 to 800. Now people are talking about 1200 kV surge arrestor because we have developed 1200 kV transformer. So to protect that 1200 kV transformer, we need 1200 kV surge arrestor as well. Okay. Now based on the energy handling capability, there are five different classes, six different classes. One is the distribution class, which is very low rating, around to 1 to 9 kilovolt, and class 1 to class 5, they have very small and very high rating, starting from 3 to up to 1200 kV surge arrestors are available. So this classification based on the energy handling capability, how much energy. When I talk about the energy, I mean how much voltage it can passes, current it can passes through that surge arrestor. Okay, so based on that, there are many two types are there. So if I do the cross section, now the materials is coming. If I do the cross section, you can see there are a number of blocks inside this who are stacking one after one. Okay, these blocks are actually ceramics. Okay, now the outside periphery is the porcelain blocks, porcelain body, and inside that porcelain body, this ceramic blocks are available. This is called actually varistor. Okay, and the rest of the part is actually filled up by a aluminum tube. And here three things are very important. Just like when I talk about the surge part, it is a kind of an impulse. So impulse is a in a sudden attack. So when this impulse immediately come and hit on the body, and that material should have certain capability to withstand that vibration. So inside that, above that block, there is a spring which actually sustain that vibration. Then the blocks are there, and in between that block there should not be any kind of gap. If any gap is there, then there is a chances to flash over through that. So you have to clean, or you have to make the surface so parallel, so there should not be any kind of uneven surface between these two top and bottom surfaces. In between these two blocks, there is the aluminum spacer, and if the blocks are filled up, then if some portion is remain, that part is filled up by the aluminum tube. Now, how do I know that what kind of height is there? Now, this mostly divided based on this is called creepage length. Now, where I'm going to install, this is mostly used for the outdoor application, and this outdoor application, this area will depend upon whether it is a highly polluted or it's a low polluted. If it is a highly polluted, then this creepage length should be as high as possible. Why? Because if it is a dust area, since the dust are deposited on the surface of this porcelain, and during rainy time, this dust will actually wetted, and there is a chances to flash over through the surface, not through the block. Ideally, when the surge will come, surge will passing through the block to the ground. It's not through the surface of the porcelain block. So in that case, your creepage length will depend where you are going to install. And if it is a polluted area, your creepage length will be high. If it is a less polluted area, your creepage length should be low. Now, if it is a high, then in that case, suppose I have some rating 400 kV block, I need 40 or 50 blocks. So rest of the area is actually filled up by aluminum spacer through which the current can flow and it will go to the ground. Okay. Now, if you look this structure, these are the different kind of classes of varistor or surge arrestor, lighting arrestor, which is available, and they have different kind of shapes also. Now this figure, if we look the bigger one, it is actually only 400. Now I am talking about 1200 kV surge arrestor, so the height is almost 3 times, and this height is normally, as I said, is the outdoor equipment. It is installed outside the and also mostly in outdoor applications. Now there is a test called seismic test. Now in seismic test, the ceramic porcelain is cannot survive because ceramic doesn't have any kind of plasticity. It's a brittle material. Okay, so they immediately it will crack. So the research, the requirement from the industry has come. The how can we reduce the height of the surge arrestor, though the rating will be same. I mean, for example, if it is in 400 kV, I need, if you look at here, that for example, 400 kV, we are using 133 blocks, ceramic blocks. If it is 1200 kV surge arrestor, they are using 400 blocks. So there is a stacking of 400 blocks. So height is so high that this normally never pass seismic test because this is a huge height. So the demand has come from industry that how can we reduce the height of the surge arrestor by increasing the rating of the block so that the number of blocks can be reduced. For example, I need the same 1200 kV block. Is it possible to make it only 200 blocks? Okay, but the rating of the surge arrestor will be remained under 1200. So how do you define that materials part here? Now, if you look at the materials classifications, there are different kind of blocks are there. If you look back that previous slide, there are different kind of classes are there. In different classes, different kind of blocks are there, and the different blocks they have different rating. Like for example, D3 block they have rating 3, D4 block rating 3, D5 block 3.4. So they have different ratings. For example, if I look this figure, I want 400 kV surge arrestor where rating is 3. So if rating is 3, that means I need 133 blocks to make it 400 kV surge arrestor. Okay, and now these different kind of blocks have different kind of rated voltage, energy handling capabilities, as well as the dimension. Now mostly D3 is defined, the diameter is 33, D4 is 43, D5 is 53. So diameter is different. Now if the diameter is increasing, that means the amount of current passing through the block is high. That's why the if you look at the diameter, as soon as the diameter is increasing, your energy handling capability is also increasing. That means the amount of current passing through the block is very high. Okay, but if you look at the thickness of the block, if the thickness is very high, that means the rating of the block is also high. That means if I need high rated, normally we increase the thickness of the block. Okay, so if you remember the previous slide that I need 400 kV surge arrestor, that means I need 133 blocks. Now if I want to increase the rating of the block, you can increase the thickness, but if you increase the thickness, again the height of the surge arrestor will be increased. So I need the same thickness with the same size but different rating. I have to increase the rating of the block. So if you look this different dimension, D3 to D5, they are looking like a solid blocks because if the surge will come, whatever the heat is generated, that is sufficient to dissipate immediately. But if you look at the D7 to D11, their size is like a polo chocolate. This is kind of there is a hole in between. The hole is given because the heat which is normally generated during the surge, that is immediately dissipated during after the surge will go back. Otherwise, in the big size, it is very difficult. If we make these solid blocks, it's not easy to dissipate the heat immediately. So what is the major function of the surge arrestor? That initially it acts as a normal insulator. As soon as the surge will come, it will immediately act as a conductor. Again, when the surge will go back, it will act as an insulator. So this part you have to remember, that initially insulator, then again conductor, then again become insulator. So how this is possible? This is only done by some material characteristic that I'll explain later. Okay, so now the ceramic blocks I'm talking about, this is normally known as varistor. This was first invented in 1969 by Matsuka, one is a Japanese scientist, and he has invented a patent which cover almost all the composition. And today I can tell, like in whole world, whoever is actually manufacturing this varistor, they are using his patent only. So this varistor is normally called as multi-oxide system. That means where it contains number of oxides. The major oxides are zinc oxides, and apart from zinc oxide, there are other 6-7 oxides are used, like your antimony oxide, silicon oxide, bismuth oxide, chromium oxide, manganese oxide, and cobalt oxide. Now, mostly all these oxide, what their exactly function is, still it is unknown, but people have made some assumption that what they are doing. Now, there are two kind of prospects are there. One is the material prospect, why this material is used, and the second is the electrical prospect, why this material is actually doing in the electrical parameters also. Now, if you look at the function of varistor, as I said, initially insulator, then conductor, then again insulator. Now, that is done only because of the presence of bismuth. This bismuth is basically a insulating oxide material, which is act as a activator of grain boundary. I'll explain what is that actually, that activator of grain boundary is. And it actually also responsible for conduction during the surge. Antimony oxide, this is mostly used for grain growth inhibitor. Grain growth inhibitor is nothing but you have to control the grain size also during the operation. And it is actually in electrical aspect, it increases the energy handling capability. All transition oxides like your cobalt, manganese, chromium, these are actually increase the non-linear performance of the surge. Non-linear means a small change in voltage, a huge amount of current will passes through that surge arrestor. Okay, and the rest of these two, silicon, alumina, they have little bit responsible for your losses parameter, which is actually very much essential. Normally, what we call the watt loss things. That is, these two oxides are very much responsible for that. So this is basically a multi-oxide system which is used to manufacturing the varistor. Now, how this is manufacturing? So normally, all these oxides are mixed together through the ball mill method. Maybe you have heard about the ball mill, which is mostly used for the mixing purpose. Then they added with some kind of surfactant, anti-foaming agent, some binder system. They make a slurry. Now this slurry is passing through a spreader. Maybe you heard about the equipment called spreader. Like this spreader is very much used to make it milk to milk powder. That is the equipment which is where it is actually used for. Then after making that powder, it is made, the compaction is done, where this kind of blocks, what you have seen, is actually fabricated. Then after that, that is matured through sintering process. Sintering is mainly nothing but the heat treatment method to improve the densification. Then they do the lapping. As I mentioned, that both the surface should be parallel. So they do the lapping through silicon carbide, abrasive material. Now, during lapping, the purpose is like the bottom plate will moving the clockwise direction, the top plate is moving the anti-clockwise direction. So this way, they do the lapping to make the surface parallel. Then they do the glass coating around the block. Now, if you look at this figure, the around the block, this glass coating is given. The purpose is because when the surge will come, there is a chances to it's called actually your screening effect. All the electrons will go to the edge of the block, and there is a chances to flash over through the side of the block. What I said earlier is like the current ideally should passes through the block, not side of the block, not side of the your porcelain part also. So it's mostly passing through that block. So that's why we do some glass coating. Glass is the insulator here again, insulating coating around the block so that there should not be any kind of decay, just or maybe the flashover, from the side of the block. Then after this glass coating, we mature the glass through some annealing method. Then we do the metallizing. Metallizing is nothing but we spray some conducting coating on the surface. Then we do block testing. After block testing, we assembled it, and then assembled we do the product testing. Then product testing, we do the packing or dispatching. So these are the overall manufacturing process of surge register. So up to here we talk about the product, how which is normally known as surge register, and how it is actually connected with, how it is actually performed. Now I'm talking about the materials part. Now I said there are two major compounds are there. One is the zinc oxide, which is around 97 to 98% is there. Bismuth oxide around 3 to 4%, and the rest of the oxide is only 2 to 3%. So ideally, this zinc oxide is this blue color, and the bismuth oxide is the red color. Ideally, all zinc oxide should be coated with bismuth oxide. Now, zinc oxide is a semiconductor, where bismuth oxide is an insulator. So if you look at the normal operating condition, as I said, it's an act as an insulator. So when the current will passes through, because of this bismuth layer, because bismuth is an insulator, because of the bismuth layer, the current cannot passes through the zinc oxide. Zinc oxide is a semiconductor, any current can passes through that. But because it is coated with the bismuth oxide, that's why it's very difficult to passing the current through that bismuth oxide layer. So you have to break that bismuth oxide layer, and then only it will passes through. So in general, if you look at the microstructure, this varistor is normally composed of three kind of phases. One is the major zinc oxide phase. The zinc oxide phase is coated with the bismuth oxide phase, and the triple junction of this bismuth oxide, there is a phase called the spinel phase. I'll talk about what the spinel phase is actually the composition part. So these three phases are there. This spinel phase actually control the size of the grain, both your bismuth as well as your zinc oxide part. Now, if as I said, like zinc oxide is a semiconductor, and it's if you look at the resistance value, it's around 10 to the power minus 2 to minus 1 ohm. And if you look at the bismuth, this is ohm meter. If you look at the bismuth, it is around 10 to the power minus 12. 10 to the power 12 ohm meter. It's a very high insulating material. Okay, so normally there are few phenomena this happen, like how this is work as an insulator initially. Okay, so if you look at the microstructure, I said the bismuth oxide is coated with the zinc oxide is coated with bismuth oxide. So when you go for the sintering, the bismuth oxide is basically low melting oxide. Okay, and this is melt at very high temperature. So when it is melted, it is actually form a liquid phase and it coated the zinc oxide grain. And during sintering, they create this oxygen vacancy. This oxygen vacancy release the electrons, and this electrons is actually it's a negative charges, and it deposited at the grain boundary of zinc oxide. So when they deposited at the grain boundary, they leads a depletion layer, and this depletion layer happens in the both side of this grain boundary. Okay, so they create a Schottky barrier. Now this Schottky barrier is around 3 to 4 electron volt, and that's why no electron can flow because of this Schottky barrier. So initially it acts as an insulator. Okay, now when the surge will come, there are a lot of mechanisms are there. There are about this mechanism, there are two hypotheses people are followed. One is the impact ionization theory. This impact ionization theory says that when the surge will come and hit on the body, all the electric field accelerate the charge carriers. Now these charge carriers collide with all lattice atoms, and this lattice collision is actually creates a electron hole pairs, and this hole pairs reduces that barrier height. So when the barrier height reduces, the electron can flow through that. Okay, so that is one theory. This is called that impact ionization mechanism. And second theory is normally called tunneling theory. This is few scientists they have reported, which says that at very high electric field, as I said, when the surge will come, the voltage is around more than 12,000 kV. And this high electric field, the grain boundary barrier becomes extremely thin, and this time this electron is, tunneling through that barrier through some quantum mechanically. Okay, and this at that time no thermal energy is required, and again that barrier height is go down, and that electron will flow. So when the surge is coming, because of this barrier, in normal operating condition, because of this barrier, no current is flowing. But when the surge will come, because of the tunneling or maybe the impact ionization, your barrier height is go down, and again the electron is flow. So this become conductor. Now, when the surge will go back, mostly it is found that the electric field across the grain boundary decreases, impact ionization stops, tunneling probability drops drastically, and all the trap charges at grain boundary, they reform and they again create the deflection layer. That means again that potential barrier is increasing. So that's again that Schottky barrier in both the side is increasing, again is become insulator. So the function is like when the normal operating condition, because of this Schottky barrier, no current is flowing, that becomes the insulator. When the surge will come, because of the tunneling mechanism or maybe the impact ionization mechanism, this barrier height is go down and the electrons start flowing. And when again the surge will go back, this tunneling mechanism as well as your impact ionization mechanism, it will actually go back, and again that Schottky barrier form, and again it will actually act as an insulator. Okay, so I said like I talk about the rating of the blocks. For example, if you remember D3 blocks, I worked on the D3 block, so I'm talking about, if you look at the D3 block, the diameter is 33 and the rating of the block is 3.6. Okay, now this rating of the block is depend upon that number of grains boundary, then your to break that grain boundary, what the voltage is required. So I said ideally all zinc oxide coated with bismuth oxide. So if I want to break one bismuth oxide layer, I need 3 volt. Okay, so if the rating of the block is 3.6 kV, that means there are 1200 grain boundary is acting as a varistor. So because to break one grain boundary, I need 3 volt. So if there are 1200 grain boundary, I need 3600 kV. Then only the rating of the block is coming 300. Otherwise, the rating, if the grain boundary is increasing, then your rating of the block is also increasing. So how do we increase the rating of the block? This grain boundary is depend upon the D. Capital D is the thickness of the block, and small d is the diameter of the grain size. So if I reduce the grain size, your number of grain boundary will be increased. If the number of grain boundary is increasing, that means you need a higher number of breaking voltage is required to passing the electron from one grain to another grain. That means my rating of the block is increasing. So the same height, same thickness, if I want to increase the rating of the block, my dimension of the grain size should be reduced. Okay, so based on that, the research purpose has come. Is normally it is found that the industry produced product, they have the rating around 140 volt per mm, and the grain size is around 12 micron. So if I reduce the grain size, definitely it will increase the breakdown voltage, and definitely it will increase the rating of the voltage. So in that purpose, as I said, the 96% of the oxides materials are actually zinc oxide. So we produce zinc oxide through some spray pyrolysis method, because it's an industrially commercial product. So I did not showing all the data here, but still I'm talking about the spray pyrolysis method. They have developed the nano zinc oxide powder with optimized size, shape, distribution also, because when I talk about nano, there are a number of parameters is coming. That things they have optimized because dimension, distribution, size, shape, everything is very much dependent on the performance of the material. So they produce the nano zinc oxide powder through some spray pyrolysis method, and they added all the additives what I talk about, like silica to chromium to manganese and antimony. These all additives, they are mixed with the nano zinc oxide powder, because 96% if it is nano, rest of 4% may not affect that much. So they mixed it properly. After mixing, they added the binder. After binder, they make sieve it. After sieving, they press it. Again, when I do the pressing, the normally people have found like what press I should press that material. So this pressing is normally optimized to optimize the grain density. Like if I press 1 ton, what will be the grain density? If I press 2 ton, 2 megapascal or 2 pascal, then what will be the grain density? So if we increase the pressure, the particles will compact each other. So density is mass by volume. So if the particle is compacting, your volume is decreasing, your mass is remains same, that means your density is increasing. So one time will come when the pressure is the maximum, and when you release the pressure, the material will bounce back. That means the volume is again increased. So when the volume is increasing, that means the density is decreasing. So that is the optimum pressure you require to get it done, to get the optimum grain density of the material. So we have optimized the material, and as I said, it's a nano material, so we have to optimize the sintering temperature also. Normally, the material is sintered around 1200 degrees Celsius, and if it is a nano, the sintering temperature should be less, because it actually helps us to increase the sintering an aspect. So we did it in 4 different temperature: 800, 900, 1000 degree, 1150 degrees Celsius. Then we these are the different reactions happened with during the sintering method. So I said there are three phases are there. One is a zinc oxide, that is the almost 97% present there. Bismuth oxide, which is in liquid phase, which is mostly happens around 950 to 9000 degrees Celsius. And the second is the spinel phase. Spinel phase is this one, Zn7sb2o12. This phase is very much critical, because I need a high dense body. There should not be any kind of leakage. Now this spinel phase actually control the grain morphology of the zinc oxide to is basically act as a suppressor. It doesn't allow to increase the grain size as well. So it reduce the grain size. Reduce the grain size means your number of grain boundaries increase. If the number of grain boundary increase, means you need a more number of voltage is required to break that every each grain boundary. That means my rating of the block is also increasing. So based on that, they we optimized the all other parameters as well, like what is the sinkage part, what is the relative density we are getting from there. Then we see the microstructure. Now if you look at the microstructure very carefully, this black part is basically zinc oxide, the white part is basically bismuth oxide. So all white part is mostly coated uniformly with the bismuth oxide, with the zinc oxide. So this is very much required. I said my previous like slide, like all zinc oxide should be ideally coated with the bismuth oxide. And the triple junction, where all three zinc oxide grains are there, in triple junction the spinel is there. So this part is the spinel. This is actually placed in between these three spinel zinc oxide grain. So this grain structure should be uniform, then only your electrical property would be uniform. So we have found the grain size around 6 micrometer. Sorry, it's not millimeter, it's 6 micrometer. And normally in industry, as I said, like we it is around 12 micrometer. Through using this nano, it directly go down to 6 micrometer. We have checked the compositions also, is almost the same what we have used. There is no kind of evaporation happen during the sintering process. We see the XRD phase also, there is no impurity phases are there. There's only three phases are there: the zinc oxide, bismuth phase, as well as the spinel phase. And then we do glass coating. Now this glass coating actually indigenously developed. This is the basically low melting glass. Earlier people using some ceramic coating glasses there, which contains lithium based composition, lithium carbonate. Now again, lithium carbonate is presently banned in market because of these global warming issues. So they started with working on the glass composition. So this glass is very low melting compound, low melting oxides. Normally glass contains either it's a boron oxide or it's a lead oxide. Lead oxide, this is very low temperature, but lead again is banned in market. So this glass oxide was made by content of boron oxide, and it was matured at 500 degrees Celsius. So they mix the glass powder with some kind of binder system. It is basically polymer metallose 400, and they optimize the viscosity, which is very much required to coat that coating of that block around that varistor, around the varistor block. So again, everything you have to optimize, like what kind of pressure is required, what kind of viscosity is required, what kind of solid content is required, because we make a slurry. So when I talk about slurry, there is a solid versus liquid ratio. So based on that, they optimize the slurry part also, and they coated it. After coating, they matured that at certain temperature, around 5 to 600 degrees Celsius. And this coating is, you can look at here, the glass is looking like white, this is the green glass. Now after maturing it becomes completely transparent. So we do again some testing here, like radiation testing, stress testing, thermal shock testing. These all actually talks about how this glass is more adhere with the ceramic body. Okay, and that is very much required, because if any kind of gap is there in between the body and the glass, then in that there is a very much chances that flashover happens through that gap. Okay, so you need certain property, like when I do this insulation, some properties required. For example, the breakdown voltage should be around 1.25 kilovolt per mm. The temperature can withstand more than 200 degrees Celsius. It should be completely hydrophobic. It should very much adhere with the ceramic block. It should have very low thermal expansion. It has very good thermal dielectric constant around 8.5, and thermal conductivity should be as low as possible, because I said it's a purely insulator material. It should not be any kind of leakage, any kind of defects, any kind of flaws should be there around the block. Otherwise, there is a chances to flush over around the side of the block when the surge will come. Okay. So after the glass coating, we do the lapping again. Lapping means we do the both the surface parallel. Okay. Then after parallel, we do the metallizing. Metallizing means normally here we spray the aluminium metal through some method where the initially tip were melted the aluminum. Then there is a pressure which actually spray actually allowed to that melted aluminum to coat it on the surface. So it is looking like exactly this kind of coated surface. We need a conducting surface, because ceramic is a basically insulator. So when a current will come and hit on the surface, there should be a conducting path, otherwise current cannot flow. So mostly in all the ceramic material, if we go for any kind of testing, you have to coat in a conducting on the surface. So we coated with the aluminum. Aluminum very good conductor. We coated it with the, we did the metallizing through this spraying method. Then we do the electrical testing. Now I said earlier the breakdown voltage was on 120 to 140 volt per mm. Now we achieved around 300 volt per mm. Okay, so almost double we have achieved, just to reduce the grain size from 12 micron to 6 micron. Okay, then we did some kind of testing, like normally the impulse testing called the residual voltage testing and high current testing. Residual voltage testing talk about like how much initial strength the body can withstand, and that is around 8 by 20 millisecond. We are applying around 10 kilo ampere current. And the high current testing talks about how the coating is useful, and how the coating is actually successful after implementing that after maturing that glass coating. So for that we need some impulse 4 by 10 microsecond for 100 kilo ampere current, and that actually talks about what the strength of that glass coating you put around the block. Then this edging test is required. Edging test is normally talks about whether any kind of leakage is happening through the blocks or not, or maybe, as I said, it's a outdoor application, so any humidity effect is normally affecting their performance or not, that also we check. And long duration test normally do how much energy handling capability, what is the energy handling capability the block should have. So if you remember the slide, for example, if I go back and say, like if you remember this block, this D3 block, the energy handling capability is 2. So if I taking 30 blocks together, the energy handling capability is 60 kilojoule per kilovolt. Okay, so based on that, my surge voltage should such that it should not be more than 60. Otherwise, it will break that surge arrestor. So my energy handling capability is very much important to go for the test to say whether the material is sufficient to keep the strength of the knot. After that, we did that assemble of that surge arrestor and make varistor and make it a block surge arrestor around 11 kV. And we have found that the rating of the block, earlier it was 3.6, now it is 7.91, or more than double. Okay, so you can look at here, just to reduce the grain size, I doubled the rating of the block. So earlier, if you remember, to make it 400 kV surge arrestor, I was using 133 blocks. So now my rating is 7.9, almost 8. So if I make it 1 to 400 kV block, I need only 50 blocks. Okay, so today people are talking about 1400 kV surge arrestor, and 1400 kV, if I make it around 8, so you can imagine that I can reduce the total surge arrestor height. So based on that, if I look at that technology aspect, like it's a new technology, people introduce the nanotechnology directly into the and people a lot of thought in the mind, like nanotechnology is only possible in the laboratory scale, but it is totally commercially implemented, commercially available. The nanotechnology was implemented, and they have found the 90% productivity improvement and 40% top line growth. Now, top line growth is little bit in a management term. I'm just expressing how it is normally defined. For example, I can produce 100 blocks per day, so, and the rating of the block is 3.6. That means in a day I can produce around 3600 kb blocks. Okay. Now my rating is 8 kb per blocks, and I produce the same blocks 1000. So my rating is 8000. So based on 8,000, earlier I was making maybe hardly 40 or 50 surge arrestor. Now I am making more than 400 to 500 surge arrestor. So that is actually give the top line growth. My productivity is increasing through using this nanotechnology. So with this, I conclude this, like using this nanotechnology. This is commercially available technology which Crompton has implemented, where you can see that how just change in the microstructure, change in the morphology, the performance of the any equipment can be changed through using the structure property correlation. With this, I'll finish up. Thank you.
Thank you
Yes.
very much, sir, for this wonderful and motivating session on surge arrestor. Your nice presentation and the way of explanation have made our participants to learn the concept in an easier way. And we are truly privileged to have benefited from your wisdom and knowledge in the domain of this surge arrestor. And
Thank you.
once again, we are thankful to Dr. Roy for giving us your valuable time for the benefit of our participant in spite of your busy schedule.
Thank
And now
you.
from the participants, if
Yeah.
anybody has any
Yes.
query, you feel
Please.
free to clear your queries from Dr. Roy. So
Please.
anybody, please come forward.
Please.
Participants, I think Palok Khandelwal raised his hand. Palok?
Please. Go ahead. Can I again share my slides?
Yes, yes. No
Okay.
problem.
Yeah. Please.
Palok? Mm. I think he is having some problem,
Okay.
but he raised his hand.
So he can write. He can write.
Yeah.
I mean.
Okay, if you are having to join with your voice,
He
you
can
can
write the
write
message.
your query in the chat box.
Yes.
No, sir. Thank you.
Okay.
And I request you, sir, to stay a while. We'll start the valedictory session at 4:15.
Okay. Okay. No
And you
issue.
are the guest of honor in that session.
Okay. Thank you.
So
Thank you.
you can leave now and again you can join at 4:15, no problem.
Okay. Okay.
And I request all the participants to stay tuned as we are having a very short valedictory session, and that will start at 4:15 p.m. sharp. So be with us.
Thank you. Thank you very much.
Thank you, sir.
Thank